is David Nolen. This talk is called Immutability, Interactivity, and JavaScript. It's going to share, if you guys were around yesterday to hear my ClojureScript talk, it's definitely going to share some ideas and concepts from that talk. I might have to cover some other material because I'm not going to expect that you were there. And this talk is also, to some degree, not just about JavaScript, but a lot about compiled to JavaScript languages. Including ClojureScript, but also JavaScript itself. There's a lot of interesting activity around JavaScript being compiled to JavaScript. A little bit about me, I work at a company called Cognitect. We are a consultancy. We do a lot of consulting work with large companies, people like Walmart, Consumer Reports. We build systems in Clojure, increasingly building more systems with Clojure and ClojureScript. We actually maintain both Clojure and ClojureScript. We also work on an immutable relational database called Datomic, which is really interesting. If you're familiar with the way that Git works, imagine a database that, again, has the entire history of all updates to the database, but you're not giving up relational queries. The big difference is that it uses data log for the query syntax, which is a very old idea. Funny enough, this talk is mostly going to be about resurfacing old ideas and trying them out in new ways. So this talk, a little bit different from the focus of my last talk, is this is very much about user interface programming. I've been doing front-end programming for a decade now. And I'm always looking for better ways to accomplish UI development. UIs tend to be extremely complicated. I think as people move more and more of their logic to the front end, people are looking for better ways to control complexity. This is, I think, a large reason why people are finally taking things like client-side MVC frameworks seriously, which they did not for a long time. If you haven't read this book and you are involved in UI programming in any sort of way, I highly recommend it. This is one of probably the best books on the history of computing that I've ever read, really. I came across it because Alan Kay recommended it on his mailing list, the Foundations of New Computing. It covers basically the people, but specifically J.C.R. Licklider, the people that were involved in sort of funneling government money towards research institutions and interesting people with crazy ideas. I think it's not too far of a stretch to say without him and the work and funding that he did at DARPA, we would not have the internet or the modern user interface. This is a photo of J.C.R. Licklider. Again, Dream Machine. It's an excellent book. He wrote two interesting papers. One was the Intergalactic Network. And that was sort of like, thinking about the internet before the internet was even a thing. The other one that he wrote, which was also fantastic, was the Man-Computer Symbiosis, which laid down the foundations for a lot of the ideas behind interactive computing. Remember, back in the day, computers were mostly used for bomb simulations or very large data processing. It's sort of like the massive institutional level. People really were not thinking of computing as a one-to-one interaction. Funny enough, 54 years ago when he wrote this, he mentions a data structure, which we're going to cover today, called the tree. And he says the tree will probably have a significant role in the future for computer user interfaces. And today I'm going to demonstrate that. I'm actually show a bunch of demos which leverage the tree data structure. It was invented by this man, Ed Fredkin, who's also described in the Dream Machine. Highly recommended. This is actually Ed Fredkin's second from the right. Really great hacker, worked on a lot of the early interactive computing systems, invented the tree. Tree is spelled T-R-I-E, and it's pronounced, he says it's pronounced, he invented it, so he says it's pronounced tree, from retrieval. A lot of times, especially if you like functional programming, you'll hear people, in order to differentiate it from T-R-E-E, tree, people will say try. But it is supposed to be tree. The second from the left is John McCarthy, who invented Lisp. Without Lisp, you probably wouldn't have JavaScript. He invented garbage collection, functional programming, programming with recursive functions, interpreters, the whole shebang. back when the state of the art was doing machine code. The other interesting thing about Lisp, which is also very old, 1957, was that it was one of the first early languages that was extremely high level. It was a symbolic programming language, but the Lisp programs could modify Lisp programs. And this was a feature that most people had only really seen with assembly. You know, you could generate instructions and write them to a memory location. In Lisp, you could do this just because it was a symbolic programming system. This is where the term, in Lisp, data is code and code is data, because Lisp source is actually a data structure itself, and it's relatively easy to manipulate. Okay, so here's another important person in interactive computing. The cool thing about somebody like John McCarthy, which really did have an effect, if you like JavaScript and you open the Chrome DevTools console and you're typing in JavaScript, right? That was John McCarthy. John McCarthy invented the read eval print loop. The notion that you didn't have to batch process an entire program, that you could interactively feed the computer one instruction at a time and see a result. John McCarthy invented that. So that's a very old idea. Alan Kay took this even further, interactive computing, because he had seen Douglas Engelbart, who was also funded by JCR Licklider's group at DARPA, well, ARPA before it was DARPA, really. They also gave money to this man, Alan Kay, when he was at Xerox PARC, and he wanted to take John McCarthy's ideas to the next level. It wasn't just about typing in symbolic mathematical expressions, which really only, is an interesting form of interactive computing for a small population. He wanted to open up interactive computing to the entire world. That meant that computers would have to be able to display text, graphics. You should be able to, he's playing a synthesizer, you should be able to play music. You should be able to see notation on the screen. It should be easy, relatively easy, for a person who is not well versed in computer science to interact with the machine. So he invented a language called Smalltalk, which is, more or less the predecessor to all modern forms of object-oriented programming. And at the same time, they also invented the modern user interface. If you boot up a Smalltalk image today, which is still possible thanks to the open source project Squeak, you can download the Squeak VM, launch a Smalltalk image, and you'll see something like this. And to me, what's most fascinating about this image is that how little the sort of UI paradigm has changed. This is an image, I think, from 1979. This is a system browser. Looks a lot like if you're used to Visual Studio or IntelliJ or Xcode or whatever. Most of the ideas around how to organize code and navigate them were derived from this system. What's fascinating about the early Smalltalk system is right around this time, they invented at Xerox PARC the notion of model view controller. As they started building UI systems, they realized they needed a clean separation in order to write composable, scalable UI programs. The idea MVC was first formulated by Trygve Rinskog, Adele Goldberg, and others. It was you can still download to this day the research note that was passed around. Long shadow. I mean, people are still building MVC systems, still prevalent. In fact, almost any JavaScript framework you would download is some variant of the basic idea. So the only sort of wrench I want to throw in this story, I actually think MVC is a relatively sound separation of concerns. You have some model that represents the domain that the user cares about. You need to present the user a view of that data, which isn't, computer gobbledygook. And then you need to have some system in which the underlying domain model, which represents what the user cares about, and the thing that they see is coordinated. Most of our time is wrangling C. And in fact, I would argue that most of our time, that problem is fundamentally a problem of managing state. The user has some visual representation of state, and they want to change it, and that needs to be kept in sync with whatever fundamental underlying domain representation you chose for the program. But I would argue that even though MVC as a conceptual thing makes a whole lot of sense, implementations leave a lot to be desired. Unfortunately, as awesome as Smalltalk is, one of the downsides of Smalltalk, for those of you that do a lot of concurrent programming in Java, is that objects are cool. They're very modular. We can easily map them to concepts we're familiar with. But if the object maintains its own state, a lot of bugs arise from this. In particular, if you're a JavaScript programmer, you know this, because in JavaScript has a very nice, simple, associative object model, but it supports mutation on it in almost everywhere throughout your program. You can even take things from the DOM, add properties on the fly. And while that flexibility is fantastic on one level, there's another level in which a great number of bugs arise from the fact that we don't have a disciplined notion of program state. So I would like to preserve MVC in this talk, but I want to show that we can actually get the modularity benefits that we like from object-oriented programming, but we can more or less throw out stateful objects. So how would we do that? That sounds like, a little bit challenging. So in order to understand this, we have to talk a little bit about trees. Trees as in the ones that Ed Fredkin invented. We have to understand how we could organize our programs into immutable data efficiently enough that we could use them to drive computer programs. And while the next section may seem very computer sciencey, companies as large as Facebook are working on this. They're actually taking the research and as well as the production work that has already been proven to work for Scala and Clojure. They're bringing this technology to an idiomatic JavaScript library so that they can make React, which is their MVC-like framework, faster and more efficient. So they're taking the tree data structure and they want to use it to make their UI programs both easier to reason about and to perform better. And this might sound very strange if you haven't looked at, been following the immutable data structure research. It's possible to, when you use them to make your program faster than it is to use mutable objects everywhere. In fact, React is slow. Not slow, it's fast. It's fast. It was faster than a lot of things, but they're losing out because they allow programmers to feed in mutable arrays and mutable JavaScript objects, which destroys many optimization opportunities. Okay, so the next series of slides is just to familiarize those of you who don't know about it, persistent data structures. And we're going to try to remove a lot of the functional programming jargon as much as possible. You don't need to be a functional programmer to use immutable data structures. That's the whole point of Facebook releasing an idiomatic JavaScript library because they want to bring the benefits of immutability to people who are more comfortable with the object-oriented paradigm. But we need to at least understand how they work, regardless of what paradigm we're going to actually use. The next set of slides are not my own. They were created by Zach Allen. Zach Allen is a facilitator at something called Hacker School, which is really great. It's basically a writer's retreat for computer programmers. So I'm going to just reuse the slides because they're great and they get to the point. So functional programming and data. So even if we're not a functional programmer, we should understand the mindset of a functional programmer. Functional programmers want to deal with immutable values. They don't want to deal with immutable objects. As we know from math, there's a lot of benefit from the notion of immutability. Computers actually support this in a very deep way, but you don't ever think about it, right? Most computer arithmetic is over immutable values. There's no such thing as changing the field of the number 1, right? You get to program and you can add 1 to 1. You know that you're not changing the original ones, and you're going to get another value 2. And so the functional programmer said, well, these mathematical properties are really fantastic, both for operations, things like adding two things together, as well as things like equality. You want to be able to test equality on values. This is a huge, for those of you that do a lot of collection-based programming, I mean, it's a massive pain in the butt to have to deal with things like, oh, somebody has a different notion of equality and I need to deal with that, or a different notion of hashing. This is all stuff that functional programmers hate. They want a simpler model. They want to have, if they have a hash map and they add something to it, they want to get a new hash map. They don't want the old hash map, the old value that the hash map that it represented to be destroyed. Okay, so this is the big idea. Change returns a new value, even on collections. You never destroy the old one. You have a bit of functional programming jargon here. People throw on the word persistent, but they don't mean persistent like persistent on disk. They mean persistent as in we're never going to destroy a previous value this collection represented. And they're fast, and this is relatively new. Things got kicked off by Chris Okazaki in 1997. He wrote a very sort of widely cited paper in the functional programming community called Purely Functional Data Structures. You can get it on Amazon. that was the first step. It took more research from actually the members of the Scala community at EPFL to come up with actually a mutable thing. And then Rich Hickey combined Chris Okasaki's ideas, Phil Bagwell's ideas, and delivered one of the very first persistent data structures that act like arrays that are not orders of magnitude slower than mutable arrays. They provide very, very good performance characteristics when compared to mutable arrays. So they're fast now, and we'll see why. Okay, in order to understand persistent data structures, all you have to understand is a linked list. It's one of the very first things you learn. You have nodes, and the pointers point to the next node. The cool thing about a linked list is that you can treat it as an immutable thing. You really can. If I have a list with 3 things, and I can set a new head, and that points to that tail, and this is beautiful. I did not modify the original list, right? I just put a new head onto that one, and I have a new logical value. I can add another head to that one that I created, and now I have 3 logical values, right? Without mutating anything. I never destroyed any previous versions of this linked list, whatever values they represented. I could, take y and x off, and then I could cons like, put on a new head, z to that, and now I have 4 really distinct values that share more than 50% of their memory, right? They're sharing memory. So not only did I not have to mutate anything, I get all the benefits of I have distinct values that I can use in my program, and it's actually memory efficient, right? There's more sharing going on here than is normal. Okay, structural sharing. This is some more jargon. So the functional programmers like to use the word structural sharing when the data structure has this property. This is a very old idea, right? So if you use Git, one of the things that's kind of weird about Git is Git doesn't record deltas. Git, when you change a file, it just writes a whole new blob. And what it does, the only thing that it actually does is a Git represents a tree. What does your source tree look at this point in time? If you change some file, it's not going to rewrite the entire tree to disk. That doesn't make any sense, right? It's just going to point to a new tree and update one of those pointers. All the other pointers to the other blobs that didn't change, they're going to be left alone. So there's absolutely nothing radical about this idea. This is the oldest trick in the book. We're just going to apply it to data structures in memory. So we're going to get space efficiency. We're going to see how we get computational efficiency. So some of you may have used immutable techniques in the past in C++ or Java, but this almost always boils down to copy on write, which does not scale for anything but the smallest data sets. We're going to see how we can avoid doing full copy on writes. So Phil Bagwell was the person that invented the data structure that Clojure modified. He invented these things called the array map tree and the hash array map tree. He wrote these papers in 2000 and 2001, I think. Anyways, Rich Hickey, when developing Clojure, he was basically wanted to write lock-free concurrent programs in the JVM. And the only way you're going to be able to do shared memory concurrency without locks is if everything in your system is immutable. So to this day, Clojure's been out. People have been building production systems in Clojure, and nobody writes locks because all the data structures that we move around between threads are persistent data structures. You don't need to lock them. So Rich took this mutable version, and he took the ideas of Okazaki, and he came up with an immutable variant called the Bitmap vector tree. It's now since been ported to Scala, as well as Haskell. There are actually versions of this in C++, pure Java, Erlang, of course, JavaScript now, and so on. The idea is data lives in the leaves in this data structure. It's a prefix tree. We'll talk about what that means in a second. And it's a bitwise tree. So what does it look like? In Clojure, we just call it persistent vector. We don't say bitmap vector tree. And the idea is what you do, instead of having an array, which of course we can't use because it's mutable, what we do is we have an array of arrays of mutable, an array of mutable arrays. Mutable arrays of mutable arrays. And we pick some dimension n. In this case, so that we can fit this onto this slide, we're going to pick a small one. We're going to pick dimension 4. And so every element of this mutable array is going to point to mutable arrays of the same dimension. And each one of these elements will point to more arrays of the same dimension. and so on. Eventually, you bottom out and you have an array, and these arrays have the data. These are the leaf nodes. Here we just have, you can imagine at the leaves we just have some numbers. And so the question is, how do you find something? Given an array of arrays, how would you actually locate a value? There's no index that you can jump right to in the same way that you can with a regular array. So in a persistent vector, this is done because there's a nice little property of integers, and that integers actually represent, there's some bit mask that it represents, set of bits. So 106, we can take the number 106. The number 106 has this 32-bit, is this 32? It is, 32-bit representation. Or it's 8-byte, yeah. Anyways, so all we have to do is mask off the first 2 bits, and this is the prefix part. This is where the word tree comes from. So we're gonna mask off the first 2 bits, and counting from 0, that's index 1. And then we're gonna mask off the next 2 bits, and counting from 0, that's index 2. Mask off the next 2 bits, counting from 0, that's index 2. Again, index 2, and now we've found our value. So all we had to do here to find this was do a couple of bit masks, and we had to do some array lookups. And this is actually really, really fast on modern hardware. The other thing we can do is if we pick the right array size and we're doing something like an iteration, these arrays can fit into cache lines. So as you iterate, the ones that are lower level, higher up in the tree, those can fit into a cache line, which is really great. So what happens is that on modern hardware, persistent vectors are actually better than they sound on paper. In the past, people talked a lot about finger trees, but for various reasons, because finger trees are not cache friendly, persistent vectors, even though they look worse, the paper complexity looks worse, they turn out to be better because of the nature of modern hardware. So how do you update something? So we want to update some value here. We can use the exact same trick that we used for lookup. All we have to do is update the path that includes the arrays that we need to change. So we just need to mutate the root. We just need to mutate the next one on the path, the next one on the path, the next one on the path. And when I say mutate, we're not actually going to mutate. What we're going to do is we're just going to copy, and then we're going to update a pointer, copy, update a pointer, copy, update a pointer. But the beautiful thing about when we copy is we don't need to change these other array references, right? So this could be a very large persistent vector, and it's going to share most of its data. So this is how we're getting the same trick that you get from linked lists. We're not going to do a lot of copy. But we're going to see if you pick a different dimension, the amount of copying we have to do is quite tiny. So after a bunch of empirical tests, both Clojure and Scala have come to the conclusion that on the JVM at least, picking arrays of dimension 32 is the best. It's the best in terms of a trade-off between lookup time and update time. To give you a sense of how nice that wide branching factor is, if your persistent vector was 7 levels deep, meaning that to find anything, it would take 7 hops, or to update anything, you would need to clone and replace 7 arrays. That's 34 billion elements. Even if this was on a 64-bit OS, on a 64-bit VM with 64-bit pointers in each location, if this was a flat mutable array, this is 256 gigabytes of RAM. And at most, right? At most, right? That's a massive amount of data. You would need 7 hops to find any piece of data, and you would only need to update 7 arrays in this massive data structure. So hopefully this sort of explains the benefit of and speed that you get from a persistent data structure. So what we're doing is we're giving up some amount of performance over a mutable data. What we're going to get is we're going to get this really awesome property where we can drive our UIs and structure them around immutable models. So the big idea here is once we have these, every place where we had a mutable model, we can now put in a immutable model. And it's not going to be slow. It's not going to be the bottleneck in your program. So I started off a year ago, or 13, 14 months ago. Maybe 16 months ago. I want to see if this could be done. So I invented a library called Ohm. It was built off of Facebook's library React. I actually, I follow the JavaScript community quite a bit. I assessed many of the different frameworks, and only only React actually had the design that would make integrating immutable models reasonable. This is really hard to do with anything else, whether it's Angular or Ember or blah, blah, blah. I mean, these libraries are actually changing. Angular is actually going to make it easier. But the point is, a year ago, it was impossible to integrate immutable data into these systems. Only React made it easy. So I built a system. I said, well, I'm gonna start programming UIs around immutable data, because I think you can ditch a lot of complexity. A lot of what we thought was inherent complexity in UIs just flies out the window if you organize your programs around immutable models. So I took ClojureScript. I work on ClojureScript. I'm one of the lead devs. I took ClojureScript and I said, ClojureScript already had a massive set. We have sorted sets, hash maps, sorted maps, persistent vectors, lists, and so on, right? We have all these data structures. All our stuff is immutable already. So now is a great starting point. At the time, there was nothing in JavaScript that provided enough data structures to write reasonable programs. And so I took ClojureScript and I paired it with React. If you're not familiar with React, React has this really nice model that's really close to how your web server works. I actually think this is why people like React. The way that React works, it's as if React is kind of like a stateless web server, right? You have some data, some source of truth, you feed it into React, and React acts like it's going to render the entire page all at once. And this sounds horribly inefficient, but doesn't matter. We like that model. We know it's simple. And so if you feed React some Noop data, it's going to semantically re-render the entire thing all over again. So the only thing that's magical about React is React says, this is the semantics that we want to deliver, but of course that's too slow. And React is quite sophisticated because it does a ton of optimization work so that what it does is it doesn't actually re-render the whole thing. It computes a diff, and it actually batches all the changes into one group and applies them to the DOM at once. One of the worst things you can do in JavaScript is be in a for loop, read from the DOM, and then mutate it. This is basically the source of any performance problem you've ever seen in a JavaScript application. People are reading from the DOM at random times, and they're writing to the DOM at random times. React basically said this just doesn't work. It doesn't scale. It didn't work for their timeline. Didn't work for really any of their applications. And people were basically micro-optimizing. So React says, no, we need to do a global optimization. We're going to actually compute the diff for the programmer, and we're going to batch them all at once. So we're not creating ridiculous amounts of jank in the end user product. Okay, so now that we understand that there's a really cool thing, if that's the conceptual model, right, for React, this means that you can actually take this diffing operation where it computes the changes. You can just simply reverse the computed DOM, right? You can just reverse these two values. And that was another huge thing that I saw that React could do. If you feed React immutable data, which shares structure, it has all these efficiency properties, all I have to do is make a snapshot. And this is not copy on write. All my previous slides were, you don't have to copy on write. Keeping a snapshot of the previous state of your app, it's trivial, right? And it's memory efficient. All I have to do is feed React my previous application state, and React can, as quickly as it moves forward in time, can compute the diff in reverse. And that was the other big idea behind OM, was that I want to demo that this could be done. If you drive React with immutable data, time travel is easy, right? Snapshotting your application state is easy. Doing infinite undo, doing tree undo, all this stuff gets easy. You don't have to compute deltas, you don't have to track them, you don't have to change your program and find the place where somebody was accidentally mutating their state. This stuff just goes out the window. You can start your program, and if you decide that you want to undo at any moment in time, you're just going to get it for free. I'm going to show a demo of OM. I show this one all the time, but if you haven't seen it, it's pretty cool. So this gentleman, Jack Shadler, who works for Ableton Live, he read my blog post, and I done to do MVC, and I demonstrated that undo for 2MDVC was basically 5 lines of code. I mean, I didn't have to do anything, right? Persistent data structures gave me undo for free. And then Jack was like, well, that's cool for to-do MVC, which is really a totally stupid thing. Nobody's writing to-do MVC. I'm going to write a less trivial program. I'm going to write a pixel editor. I'm going to use OM, and I'm going to see how hard it is for me to do undo. He's a very experienced UI developer, and he wanted to verify that my claims were true. So what he decided to do was he wanted to represent this 64 by 64 pixel canvas And instead of using a mutable array, he represents that canvas with a persistent vector, the same data structure we talked about earlier. He stores each element of that 4096 element vector is a color code, a string. Let's see this in action. Okay, so let me make this bigger. All right. So here it's a nice little UI. I can pick colors here. I can make a little circle. I can do this. And on the left, you should see that the history is accumulating every time I paint a complete stroke. You're getting something. So on. I could do this all day, right? And then if I click here, there's the undo, and that works. And I can redo, and that's going to work. And I can even scrub over this, and you can see the preview on the left. Works. And so at the end, he tallied up how much code he had to write to make this functionality work. And this is the entire file. It's 60 lines of code for everything I just demoed. Undo, redo, and as well as the scrubbing playback. Again, here you have the app history. Let's zoom into this. Oh, well, it doesn't really let you zoom in. But anyways, if you can see here, all the app history is, it's just a mutable reference which stores the snapshots. So in order to do undo, all he's doing is he's pushing snapshots onto a stack. When you click undo, he's just popping off those off that stack and putting them back onto the redo stack. That's the only thing he has to do. Immutable data structures take care of the rest of the thing. Here he's got the code, 3 lines of code for updating the preview. There's one function for watching the preview area. That's it. I mean, there's nothing, right? And this is not a small application. This is a large application. It's like 2,500 lines of ClojureScript, right? So he spent a lot of time making it be a fairly nice, sophisticated pixel editor. But the thing he didn't have to do was waste any time building an undo system, right? Because he picked the right data structure, something that would have generated a lot of complexity in his program, that just disappeared. That wasn't a problem he had to consider. Okay. So for those of you that care about memory, so this is using the Chrome Dev Profiler, which is super useful. If you've never used it and you have memory problems in your program, I highly recommend turning on their Heap Snapshot Profiler. So what I did here was I basically loaded up his editor, and I basically said, I'm going to mutate the vector. I'm going to make 1,000 edits. And I'm going to see how much larger the heap is after I've done this than when the app started. So the heap, when this application boots, is 3.8 megabytes. After 1,000 snapshots of the canvas modified, it's only 0.2 megabytes larger than when we started. On the right is the same thing, but instead of actually using persistent data structures, I took an array, a JavaScript array, with the dimension 4096, and I copied it. I made an edit, and I copied it 1,000 times. You can see that it takes 1.7 megabytes. So it's nearly an order of magnitude more memory efficient to use persistent data structures for managing your application state than it is to record, to actually do something based on copy on write. You could also do this, of course, you could compact this with deltas. But the beautiful thing about persistent data structures, that it's not the same as deltas. In Ohm, I can pick any point in time and jump back to it, right? If you're going to do deltas, you're going to have to play back the log. The log has to be played back. With persistent data structures, if there's some point in time you need to return to, you just feed it to React, and you're going to go there. There's nothing else to do. There's nothing to play back or reconstruct. So there's so many apps. I mean, it's like there's tons of cool apps that people build with Ohm that benefit from it. One that I demoed yesterday is really cool by CircleCI. They're a continuous integration server, and they actually have this amazing capability because their entire app state is immutable. They often need to coordinate with designers, and they often are like, I need you to open this in Firefox, and they're in the middle of some 10, 20 steps to find the bug, right? And the way that they did it, they can actually press a key command, because the app state actually encodes the entire state of the app, right? It can serialize to a string, copy to the clipboard, they can open up Firefox and they can paste that string in, and the app is booted into the exact same state, even if you were in mid-key press, right, in an input field. You can hydrate your entire application in any browser from whichever browser you found the bug in, which is pretty awesome. There's another cool app that's quite new that I think is pretty cool that I recommend checking out, especially if you have teams and you need to prototype. This is a really cool new thing called Precursor. It's a prototyping application. You can see in the background they're building some window or whatever, what have you. And this is all written in Ohm. They built their whole thing in Ohm, and it's real time. You can share your prototypes on your team. It's pretty cool. Okay. So again, this is while this might sound like really bleeding edge, other people are working on this problem. So for us in ClojureScript, we use React, we use Ohm, there's other things like Reagent, Quiescent, and so on. So we're already on board for this party, and people love it. But none of these ideas are specific to ClojureScript. It's not like ClojureScript has a stranglehold. This is just computer science. So Facebook has taken all the ideas of the persistent data structures I talked about earlier, and they now have an idiomatic library you can use from JavaScript called IMMUTABILITY. You can feed this into React, and all the things that I demoed are possible today. There are even entire React-based frameworks that more or less copied the way that Ohm worked. There's one called Omniscient. Omniscient is more or less Ohm, but you can use plain JavaScript. Very cool stuff. And then there's some other interesting things that you will encounter, which at Cognitech we encountered pretty quickly since we were already on board with immutable data. And one of the big problems you'll encounter is that, while that's great when you're on the client designing your programs around immutable data, that doesn't solve the problem of marshalling immutable data to the client itself. Almost every web server that just does plain JSON, and what you're going to get back are not the models that you wanted, right? You're going to get back JSON, which is unideal, right? What's nice about JavaScript objects and arrays is that you can take them from the server and you can feed them into React. That's actually really cool. But if you want to replace that with immutable data, you got to do something else. And so at Cognitech, we solved this problem. And we have this thing called TransitJS. You can get it on, it's on Node. If you use AMD, you can use that. If you want to use a script tag, you can use that. What Transit does, Transit encodes in a very efficient way an extensible data format into JSON itself. And so here I show that you can actually make a reader for JSON, right? A reader for JSON. So you can actually interpret JSON, and instead of getting JSON objects and arrays out, you get back immutable JS maps and lists, right? So, and the way we've designed it, it's very efficient. There's a lot of, it's gzip friendly. We do caching for you. So one of the big things about JSON responses that people put up with is that you have redundant keys. You repeat the keys over and over again in your query results. And so Transit doesn't do this. Transit actually, once it's seen a key once, it replaces it with 1 or 2 characters. And this makes the payload, 40% smaller. That means, and we also encode everything as JavaScript arrays. We did a bunch of benchmarking. Even objects are encoded as arrays, and this parses faster. We can actually parse TransitJS, the same logical payload in Chrome, faster than you can actually parse the JSON, which is pretty wild. Anyways, I recommend checking out TransitJS. There'll be links for this stuff at the end of the slide. People are using this, so people love this. So people are taking, again, this is not about ClojureScript at all. People are taking React, they're taking the ideas from Ohm, and they're hydrating their applications with TransitJS. They want to be able to feed immutable data directly into their app and have it ready to go. Here's some links. I highly recommend checking all this stuff out. Again, look at ClojureScript and Ohm. Even if you don't intend to use it, it will probably lead you to, if you're heavily invested in JavaScript, to related JavaScript projects. There's links for TransitJS. There's also something called Maury, which I maintain. Maury was actually Back in the day, before people thought immutable data structures were cool, I actually wrote Maury 3 years ago. All Maury does is it takes ClojureScript, compiles the standard library, and exports an API for normal JavaScript use. And there's a lot more interest in it now because while immutable.js is actually really, really solid, Maury is just older. It's just been around longer and it has more functionality. So there are still lots of JavaScript folks that end up using Maury. Actually, Meteor.js uses Maury. They actually had a problem with their dependency graph algorithm where they realized that they were doing a lot of copy on write, and they just replaced that with Maury to get whatever, 100% performance boost. So yeah, that's about all I had. I think if you guys have questions, feel free to ask.
In an application that is data bound, and JavaScript being largely a series, right? What are some of the distinct advantages that immutability has in that kind of context? The immutability there is fairly controlled.
So the question was, what do you do? So the thing is, data binding is really popular in JavaScript. There's lots of frameworks use data binding. And the mutability there is controlled, I would say, only in the sense, I mean, having built a lot of these systems and tried them, it's only controlled in the sense that you propagate changes. But the thing that I don't like about these systems is that they end up being, when your application gets large enough, when you do a lot of data binding, you now have implicit dependencies, right? So something changes, and then something else changes 5 steps away. And where, how, who bound what, when. And actually React, they actually used to use a data binding system based on Backbone. They replaced Backbone with React because they were tired of debugging systems where you didn't know who changed the state. In React, people actually, I mean, again, you have to look at React in order to get it, but React doesn't support data binding at all. It's the idea you feed data in and it computes some view. There are no listeners on the data. If I feed different data, it's just going to generate a different view. And the reasoning benefits for that, I will say, has to be experienced to be understood. Especially if you've done the other thing, you definitely need to try React and see the semantic benefits you're going to get by not having to walk back the trace of who's bound to what through what events.
So pardon that this was one of the first things to talk about, came a little late, but you mentioned like immutable arrays in JavaScript. You can't really control the active browser's data structure that you use. I'm not really sure what you mean by that, how you make it. Or is it just the algorithms that are produced just don't change the array? I'm assuming that's what this is coming down to.
So I think the question was, the question was maybe trying to clarify how this is done. No, these are just custom data structures, right? That's all that they actually are. They're just custom data structures. You can't use them as arrays. In fact, if you look at immutable.js, the API is not the API that you use for arrays. It's not the API you use for objects. It's just a different API. Other questions? Cool. Thank you.